In this video, we're gonna solve example 3. We just did example 2 in the previous video. So assuming if you're using that same worksheet on the calculator, be careful here because you are starting a new example and the variables and formulas need to be symbolic. So let's look at TR right now. It's got all these things that don't belong to this current problem of example 3. So if you insist on using the same worksheet, what you should do is do a clear AZ, which clears all the variables, single character variables from A to Z. Then you look at TR again. Then it becomes clean again because F and K are now just symbolic variables. Let's check to be sure. Okay. Now let's look at this example here. You have a car modeled as a spring mass damper system going across a bridge whose surface has become a slightly sinusoidal shape because of a creep of concrete. Let's not forget that in the very beginning of this course, we mentioned that, okay, let's go back and look at that. We can move to any inertial frame of reference and state our equation of motion in Newton's laws. That was a basic fact of dynamics. So here, this is very important here. If you are moving at a constant velocity from an inertial frame, then this new frame is also inertial. And you can build your coordinate system in this frame, even if it's moving. So now let's apply that knowledge to our current situation. So let's go into the frame of the driver. Actually, I should say an observer who's moving horizontally at the same speed as the driver. However, the driver is going to be experiencing up and down motion, while the new observer of the new coordinate frame does not go up and down. Okay, otherwise it's not inertial. So it is having a fixed height, but moving across at a speed of 72.4 kilometers per hour, which is the same as the vehicle speed. In that frame, in that moving frame, what do you see? Well, what we see is moving ground, right, of amplitude 3.05. And what is the frequency? Think about it. In the frame of, in the moving frame, how soon will you experience one complete up and down? Okay. In other words, when you hit this peak, when is the next time you hit a peak of the ground? Well, the two peaks have a separation of L. The speed is S. So I hope you're convinced that S over L is how many complete cycles you receive, right, per time. So that is the frequency. But be careful to use consistent units, okay? And that, again, will give you big omega, the driving frequency of the graph. And we have 40% damping here. And we also have the stiffness of the spring given indirectly by a static test. So you cause this much deflection when you apply this much weight. So spring constant is easily determined. So we can go to our discussion. Okay, so now first let's be sure that all those things M, K, and so on have not been defined yet. So now let me put in the mass, which is 14 kilograms, okay, which is given in the picture. Now, how do you determine K? Well, K was given experimentally. So let's take a look at it again. When you apply some external weight of so many kilograms, you cause so much deflection in cm. So be careful with the units here. Okay, so 45.36, that's in kilograms. So multiply that to 9.81 with the amount of newtons applied to that car. And that turned out to cause a deflection of 2.03 cm, which is 0.00203 meters. So in newtons per meter, it's this much. And omega 0 then, since K and M are both determined, we can compute it as usual. It's the square root of K over M. So this is a number. And the span is 12.2 meters. And after colon, you can put multiple input on one line. The speed is, be careful with the units here again, 72.4, which is in kilometers. So multiply that to 1,000 meters. And that's per hour. So that's 3,600 seconds. So that's our speed. And what about the input frequency? Okay, that's called omega here. Well, it is 2 pi. Now again, be careful where you find the pi symbol. It's here, 2 pi. That you can skip the multiplication sign. Times the speed over the span. Speed over the span is the frequency f, right? So 2 pi times that is the angular frequency, or frequency in radians. It turns out to be this many radians per second. And now, since our PR formula is already entered, you don't have to do it. But if you're starting a fresh calculator page, then you have to type in this formula and store it into TR. Now let's define B in this formula. B, which appears in this formula, it is a frequency ratio of big omega over natural frequency omega 0. So it's a numerical value here. Now let's check TR. It has become partly numerical. Okay. And then let's put in Z. The damping ratio is given as 40%. So that's going to change TR. TR is recalculated automatically. It's 1.6 something. So in order to know what is the maximum deflection of the mass, we just multiply TR to the ground deflection amplitude, which is 3.05 cm. So the answer will be in centimeters. So it's about 5 cm, which is the maximum response. And that answers the question. Okay.